Hey guys, welcome back to another week of New Horizon tutoring videos. If you don't remember, my name is Liz, and again, today we're going to be going over some math. So if you don't remember, you're just going to need your math packet from NHT, a notebook that you've been working out of, and a graphing calculator, obviously something to write with. But yeah, we're just going to go ahead and get started for today. We're specifically going to be focusing on page 6 out of that book. Not necessarily everything within that. Just kind of like the middle portion, I guess, specifically focusing on circles. We will be talking about like equations of circles a little bit later, but we already even like went over conic sections. So if you remember that at all, we talked about circles for a little bit in there. That was the first conic section that we talked about. So it's obviously going to be kind of a similar concept because circles are always circles. But in conic sections, we typically talk about circles in terms of them on a coordinate plane. Now we're talking about circles in terms of basic geometry a little bit more. So it won't be super basic. Don't let like basic geometry kind of fool you into thinking it's going to be easy. Just because this is kind of a more difficult portion on the ACT. It honestly just kind of depends on like the specific questions that they ask over circles. Today we're going to be tackling tougher questions. And then next time, if we have to review the notes a little bit, we will. And then we'll probably get into a couple of easier practice questions that are going to be in the test, because those still are important, even though they're not as complex as the ones that we're going to tackle today. And then we're also going to talk about, again, the concept of like revisiting equations of circles in that sense. So a different kind of spread of questions, but all based around obviously the same idea of circles. So yeah, we're just going to go over that. The breakdown for today's class is going to be maybe like 10 minutes of notes because it's really not like too horrible going over the notes in the packet. Just kind of the basics of that. And then some practice questions. And like I said, the practice questions are going to be a little bit more difficult. It covers some concepts about circles that aren't in the packet, which I definitely want to touch on because they will be in the ACT. So obviously, if they're in the ACT, stuff you guys need to know. But yeah, if you're lost while we're going like through the practice questions or like as I first write it up on the board, if it seems kind of like totally out there, don't feel discouraged because there are more complex topics about circles. But yeah, with that in mind, we're going to get started. Again, just going over notes to start with on page 6 of the ACT Math packet. Okay, so this is what we're going to talk about first. So obviously just going over the basics, draw my basic circle there, and we have a couple equations that we need to go over. Again, if this seems like a review, it's because it probably is. This stuff isn't too difficult, but it will get more complex as we go on, and these are just some basic topics that we need to revisit and make sure we have down. So yeah, here we have our circle. The biggest thing that I labeled is going to be the radius. We just call that R. The radius is, in its technical definition, any line drawn within the circle that spans from the center of the circle to the outside of the circle. So in essence, there's like any number of ways that you could draw this radius. We just drew it like that for that one, but it could be over here, over there, any way you want. So that is the radius. In dealing with the radius, we are able to derive a couple equations that are really important, very essential. The first one, this isn't necessarily, I wouldn't call it like an equation, it's kind of more just a relationship. That marker is dead. So we'll just stick with this one. Figuring out the relationship between the diameter and the radius. So if you see here, we have our D, stands for our diameter, is equal to 2 times R. So basically what we're saying is that the length of our diameter is going to be twice the length of our radius. So that might beg the question, well, what is a diameter? The diameter in the circle is essentially, again, any line drawn within the circle that spans from 2 points on basically the opposite edges, and it has to cross through the center. So it's going to be basically the biggest line that you can draw within the circle. Typically in dealing with like equations, we deal a little bit more with the radius than the diameter, but like I said, it's important to know the interchange between those two. So if you think about it, a radius is essentially broken up into 2 equal parts marked by that center, where there's like one radius here. Add them together, that's 2r, which explains that equation up there. So basically our diameter is going to be 2 times long as our radius for any circle that we're dealing with. So that's that first equation. Our second equation deals with what we call circumference, which is really just a fancy term for the perimeter of a circle. So if you remember, the perimeter is essentially the 2-dimensional space around any polygon. So we've dealt with it with like squares, rectangles, triangles, all that jazz. For a circle, it's a little bit harder, right? Because it's not composed of straight lines, obviously. It's one like smooth curve that forms together to form a closed figure. So if we think about it realistically, it'd probably be pretty hard to like measure it. So that's why we're dealing with this equation here. For other perimeters, let's say for example a square, we would just add up all the sides. We can't add up all the sides here. So luckily we have some relationships that we have to deal with to find the circumference of our circles. The most common one is going to be 2 pi r, which basically just means that you find the product of 2 pi and the radius. That's going to be your circumference. Or if you want to think about it in this fashion, we know that 2 times our radius is equal to the diameter. So depending on what they give you, you can really use either equation interchangeably. Just make sure that you're plugging in the right value, right? For either your radius or your diameter, depending on what they give you. Another kind of side note with this pi value, it's 3.14, you guys probably already know that. There's like a pi button actually on your calculator. But when you are taking the ACT, just be wary of the format that they want it in. Depending on the individual question, it might use like the 3.14 taken out and just like round it off as a decimal, or it could keep that pi in there. So before you actually evaluate it on your calculator, just make sure you're checking the answer choices so that you don't have to do more work than you have to, and just make sure that you kind of have it in the right format depending on the answer choices for the specific question. So that's the circumference, not too difficult. Again, just the space around the outside of the circle. Next, we're going to talk about the area, which is the 2-dimensional space inside of the circle. We've talked about that before in other regards with other shapes. This time, again, we're using that concept of pi, and we're having the radius be squared. So it reads as area is equal to pi r squared. You've probably heard that before. Again, you might keep that pi in there, might not, depending on the answer choices. And notice that there really is no way to integrate the diameter into this one. It has to be the radius. So just be very careful. If they give you like the diameter measurement of a circle, make sure you're dividing it by 2, getting the radius, and then plugging it into this equation to find the area of the circle. Okay, one more thing I want to mention based on this diagram. You'll see this come up often in ACT questions regarding circles. It's what they call a chord. So a chord is kind of like a diameter, but with less rules. It is going to span the entire length of the circle from any 2 sides, but it doesn't have to go through the center line. So we just call that a chord. It's contained within the circle again, but it doesn't have to go through the center. So if you want to think about it in this way, our diameter could be called a chord, right? But it's just a special chord. It's actually going to be the longest chord on the circle because it does pass through the center of the circle. And since it kind of has like a fixed definition that we already talked about, that's why we're going to deal with it often in like solving problems and using it for our equations. Okay, one more thing that I want to talk about in terms of the basics of circles. This is also on your sheet. It basically just reads as the number of revolutions is equal to the distance traveled divided by the circumference. So you could think about this in terms of like a wheel on a bike, where you travel a certain amount of distance, and we know that our circumference has a set amount of length depending on what your circle actually is. So as it goes along that length, it's like touching every point of the circle. So if you want to find the number of revolutions, or basically the number of times that that circle turns over that distance, you're just going to take the distance that you travel and divide it by however long your circumference is, and then obviously dealing with these two equations for your circumference. Okay, so like I said, that's the basics for circles. Kind of based off of that information, we're going to get into some more specifics, dealing with what we call sectors and arcs. Okay, so like I said, now we're going to talk about the concepts of arcs and sectors. The first thing that we're going to talk about is an arc. So we have what they call AB. It also can be denoted like that with a little curved line above it. And that's going to be what we call an arc. So essentially an arc is just a portion of the circumference. So it's dealing with that equation C is equal to 2 pi r, or C is equal to D. So let's say we're dealing with like a pizza in this sense, a circular pizza. Our arc would be thought of as like the crust, just the outside of it, obviously. So like if you were to take a slice of that pizza, your arc would be the little crust part that you have of that. It's a cheesy analogy, no pun intended, actually, but it makes sense. Okay, so for our intents and purposes here, I'm just going to call the length of that arc x. And basically what we're going to do is we're going to be able to set up a proportion based on just general relationships in circles in finding that x. Okay. So this is the proportion that we're going to use. So we have 2 pi r over 360 is equal to x over theta. So might seem kind of weird. We're going to break it down. Basically what we have is a comparison between the entire circumference of the circle over the entire angle measure of the circle. And we're comparing that to our arc length, which, like I said, is just a portion of the circumference. And we're comparing it to what we call theta in this sense, which is just going to be the measure of our central angle, which makes sense realistically and logically, because every circle, no matter the size, is going to have 360 degrees, right? And every circle, no matter its size, the circumference can be represented by 2 pi r. So like I said, we're taking the whole circumference over the whole degrees contained in a circle, and we're comparing it to our tiny little section that we want to look at and the angle that it's represented by here. So what we're going to use in order to solve this is what we call the law of proportions. Where essentially, as long as you know this proportion, it's very important, I would recommend committing it to memory. What we can do is plug in any of the 2 out of 3 variables that they can give us, whether that's r, x, or theta. We can plug in any 2 of those 3 and then cross multiply the numerator of one, denominator of the other, numerator of one, denominator of the other, get an equation and just use simple division to solve it out for the one variable that we are looking for. Again, it really doesn't matter as long as you have 2 of 3 variables, you can figure out the other one in this sense. So like I said, that's dealing with arcs. Now we're going to deal with another related topic called sectors. Okay, so the way that they're going to kind of denote what a sector is in this sense, A, O, B, where we have A here, O here, B here. As you can see, that clearly sections off what portion of the circle we're talking about. And so up here, when we dealt with arcs, we were dealing with the circumference, right? Now, for sectors, we're going to be dealing with area. So we're going to have essentially the same proportion or the same structure to the proportion. The values are just going to be a little bit different because we're not talking about the same thing here, right? Before we talked about arcs, now we're talking about sectors. So we got to change it up a little bit depending on what information we need to get from it. So I'm just going to go ahead and write out that proportion in a second. But if we want to go back to our pizza analogy, here we have a piece of our pizza, and now it's going to be like, instead of the crust on the outside, the actual pizza on the inside itself. Okay, so like I said, these 2 proportions that we set up are almost identical. This one value up here is just what's differing, right? Because we're changing from our circumference to our area. So now it reads as pi r squared over 360 is equal to x over theta, where x is going to be the area within our sector, which logically makes sense because we know that pi r squared is the formula that we use to find our area. We're still studying it over 360 degrees. That doesn't change within circles. We really just kind of had to like change what x stands for. So now x is standing for, like I said, the area within the sector, and theta stays the same. It's just going to be the angle that is in reference to. Okay, so that is essentially it for sectors, arcs, stuff like that. I don't think that there are actually any problems dealing with sectors and arcs in this specific section, or this specific session, but there definitely will be next time, just kind of revisiting that idea. But again, the biggest thing with that is, one, to be able to recognize, okay, are we dealing with sectors or arcs? Because the procedure is going to be a little bit different. And 2, just being able to memorize these equations. The reason that I say memorize is because if you understand a logical relationship within these 2 equations, it's pretty self-explanatory. You don't necessarily need to like commit it to memory. It makes sense logically. So as long as you have like a general idea, it shouldn't be too difficult to recall this. Okay, awesome. So now that's kind of all the notes we're going to go over. We're just going to go over some practice, and yeah, we'll just work through it like we have in the past. So this just reads as find the measure of arc QR, where we have our circle here, and we have a triangle circumscribed in there with points P, Q, and R. So what we're looking at is this arc length here, and we're given two angle measures. Q is going to be equal to 110 degrees, and R is going to be equal to 30 degrees. So yeah, we just have to find the measure of that arc QR here. Okay, so hopefully you guys wrote that down. Now we're just gonna go over how to actually solve this problem. So I guess this one, I kind of fibbed. This one is dealing with arcs, but it's not dealing with the law of proportions. It's dealing more with angles, which angle measures in circles are gonna be a big topic on the ACT, super important. And I know when I was taking the ACT personally, I struggled with this concept. I don't know if it's just because they didn't go through it in school, I don't know. But I just found this difficult to understand, so that's why we're gonna go over it. So what we're gonna look at first is this triangle in here, right? And we're gonna recall our knowledge of triangles. So we know that every triangle, regardless of shape, size, composition, the angle measurements are all gonna add up to 180 degrees, which is good for us that we know that, because we are given two angles out of the three here. So simple math, we're gonna be able to figure out that the third angle of our triangle. So I have 110 plus 30 is gonna give me 140 degrees. 180 minus 40 degrees is gonna get me 40 degrees for this angle here. Okay, so that process is relatively straightforward, right? Not too difficult. But now we really have all of the information that we possibly can about this figure. So now it's really just, what do we do with the information that we found out and that we've been given? And that really just comes from knowing relationships between angles in circles. So it seems relatively straightforward once you kind of learn the relationship between angles in circles, but there are a lot of different relationships. This one is just one of the simpler ones. So if we have basically like any angle measure here, and we have these two ones that are like still on the edge of the circle, this angle measure here is actually going to be equal to the angle measure in the triangle opposite it. So the measure, like the angle measure of our arc QR is just going to be 40 degrees, which just make sure that, like I said, you know the relationship between that and how we got to that, not just thinking to yourself, oh, we figured out that this was 40, so it must just be 40. You can't think about that way, but that's not gonna serve you well in the long run. Make sure that you're able to kind of like visualize that and see why. And I guess if we want to think about arcs a little bit more in terms of like measuring them, there's kind of two measurements that we can talk about. We can talk about the actual circumference, or we can talk about the angle measure that they're held in. The reason that we can do that in terms of circles and not in terms of like other polygons or other figures is because of the nature of circles. Just the fact that they're always going to be equal to 360 degrees. So it's kind of like thinking about this small portion out of 360 degrees. It's kind of like if we were dealing with a theta in there. So yeah, angle measure of, or arc measure of QR is going to be equal to 40 degrees in this case. So it gives us a little bit of information and it gives us a diagram. It just says that the chord within the circle is bisected by a segment starting at the center, and it wants us to find the radius of this circle, where the entire length of this chord is going to be 18, and that small segment is going to be 6. Okay, so we're going to go ahead and go over this problem. I vividly remember doing one of these problems in Manoj's classes when I used to take his ACT class before I started working for him. And I remember that I was just so confused. I was like, there's no way we're not given any information about circumference or area. I was like, there's no way you can figure out the radius by given all of this weird tangential information. And then he drew one line and I was like, oh, yeah, that makes more sense. Because when I drew my radius, I was like, oh, I can just draw my radius wherever I want to. My radius is gonna look like that, which is not incorrect to say that. But in knowing that we can draw our radius any way we want to, why wouldn't we draw it like that? And now we're dealing with a triangle, which it definitely is a reoccurring theme that you are gonna see crop up in dealing with circles, that we deal with triangles a lot as well, which seems kind of weird, but it works out and we're able to use the relationships between the two to figure out information about circles. So now basically what we have is a Pythagorean theorem question. This is gonna serve as our x because that's our radius, we wanna know what it is. And it's also nice because we know that this chord here this segment is bisecting the chord. So therefore, if we know that the whole chord is equal to 18, we know that each segment is going to be equal to 9. That's just simple. 18 divided by 2 is 9. And also, it is a piece of information that you ought to know that if you ever have a chord anywhere on a circle, and you have a segment that bisects that chord and starts from the center of the circle, it's going to bisect that chord at a 90-degree angle. So even just by the figure, you probably could have guessed that that was a 90-degree angle, but make sure that you actually know the relationship between that. And a key word is bisect. So let's say that this small segment here didn't bisect the chord, it was just drawn to the chord, then it would not be at a 90-degree angle, right? Because let's say we have this line there, obviously that's not bisecting the chord, and obviously it's not at a 90-degree angle. So just make sure that you know the actual logic and relationship behind that. But now we're just going to use Pythagorean theorem, solve for our x. So if you remember Pythagorean theorem, a squared plus b squared is equal to c squared, where a and b are going to be the legs of our right triangle and c is going to be our hypotenuse. So now we're just going to plug in the information that we've been given and solve for our hypotenuse x. And then we're left with x squared on one side, so we're basically just going to take the square root of that. So then when we do that, we're left with 117 is equal to x, or square root of 117 is equal to x. But if you've ever dealt with relationships with square roots, we know that we can actually simplify that down because we can write it as 9 times 13 is equal to x, and we know that 9 is a perfect square, right? But 13 is not a perfect square. So we do that operation, square root of 9 is 3, and we have to keep that 13 in there. So that is going to be the length of our radius, and then obviously whatever units we've been given. More likely than not, they will write it like this. They don't want it like this because it's not solved down as simply as it can be. And they also really don't evaluate weird numbers to round off as a decimal. They want it to be as precise as possible. So that's why we're going to be working with 3 square root of 13 in this case. Okay, so now we will probably have time for 1, maybe 2 more questions. These 1 or 2 are going to be dealing with, again, just more of the angle kind of portion and relationship with circles. so here we are given our diagram, and again, dealing with triangles again, but we have a circle and a triangle formed by two tangent lines here. CB and AB are going to be our tangent lines. We are given an angle measure here, an angle B represented by 30 degrees. We're told that AB and CB are going to be congruent in length, and it wants us to find the measure of angle ADC here. So yeah, that's basically what we're going to be figuring out. So if you want to think about it in that sense, we're basically just dealing with like angle measures of arcs again. Okay, so a couple disclaimers. First thing that you need to know is never rely on what the figure looks like, because they're never going to be drawn to scale. Might look like it's drawn to scale, but don't rely on that for your answer. So like in this sense, it looks like AD or AC is going to be a diameter, right? So we know that if a diameter splits the circle into two equal parts, this would be equal to 180 degrees. But it doesn't actually tell us that AC is a diameter, so we can't rely on that just because it looks like it in this sense. So we're actually going to have to do a little bit of mathematical manipulation here. And again, we're going to deal with relationships of triangles to get to our answer dealing with circles. So what I'm going to look at here is this triangle first. So it's basically going to be an isosceles triangle, right? We know that isosceles triangles have two congruent sides and that their respective angles are also going to be congruent. So in that sense, this angle is going to be equal to this angle, which is nice because we know this angle here, so we can figure out the measure of those two angles. So basically, I'm just going to take 180 degrees. Again, all of the angles in a triangle are going to add up to 180 degrees. Subtract 30 from it, that gives me 150 degrees. 150 divided by 2, because these two angle measures are congruent, is going to give me 75 degrees for both of my angle measures here. Okay, so now this is really another important relationship that you ought to be able to know in this. Basically, what we have here, and I'll admit my figure is not the best drawn it probably could be, but we have kind of like two different sides of our circle. We have this side represented by the angles here. These two angles here are 75s, and we have this side here, which is what we want to know. So a relationship that you need to know in this case that we're going to use deals first with just the sum of all of the angles in a circle in general. It's going to be equal to 360 degrees. Obviously, we know that. So what I'm going to say is that it can be, like I said, it's going to be represented by two sides, right? 75 and 75. And whatever the measure of this portion is, I'm just going to call it x. So here, now we have a very simple equation. 150 technically over here. If we subtract that over, we get 210 is equal to x. So that essentially is going to be the angle measure over there. That's going to be our final answer for that. Okay. Let's see. I have one more question. It's like pretty related. So we have 5-ish minutes left, so I'll go ahead and go over that quickly. Okay, so yeah, I'm just gonna go ahead and kind of like work through this problem and just show you the relationship rather than give you something to solve because we really only have like less than 4 minutes. So basically the problem tells us that the angle measure of Q is equal to 70 degrees. and PQ and PR are congruent in length. So again, we're dealing with an isosceles triangle here. And it wants us to find the angle measure of AOB, so this angle measure here. So basically it's the same exact thing. Since I know I have an isosceles triangle, I know that these two angle measures are going to be congruent because they are the respective angle measures of the congruent sides. So then basically what I'm going to do is I'm going to move this line up here, and by this line I mean the bottom line of my triangle, because the relationship is going to stay the exact same because you're really just shifting it up. So this is still going to be equal to 70, and this is still going to be equal to 70. So then basically what we're going to do is kind of transpose that onto the circle. So if we know this is 70, this is 70. 70 plus 70 is going to get us 140 degrees for this arc. And since we know that our arc length is going to be equal to 140 degrees there, and our arc length is basically characterized by the angle measure that we want to find, angle measure AOB, that's also going to end up being my answer for this problem. So again, very similar concepts dealing with like triangles inside circles and the relationships between that. It really just comes down to the relationship between kind of like the central angle, the angles of the triangles, and the arc measurements in there. Okay, so we are at 40 minutes essentially. That is our time. So I hope you guys learned something today with circles, all that jazz. And yeah, we're basically going to be doing similar concepts. Next time, we're just going to quickly revisit the idea of equations of circles. So getting a little bit back into like plane geometry with that. And then, or not plane geometry, coordinate geometry. This was plane geometry. Coordinate geometry with that. And then we're going to do some more practice problems that will look similar to this. Again, just continually integrating the same ideas that we're going over, making sure that we're able to apply them on problems that will show up on the test. Okay, so that is the class, and I will see you guys next week.